first time I am teaching this topic in the current format of a 1-hour kind of standalone talk. The previous times I taught this topic was always to a group of students who had already listened to 10 hours of geometric deep learning material. So I'm trying to deliver this material in a way that won't assume too much prior knowledge, but I'm also not completely sure what the timings will be like. So one thing I said to Anir earlier today, in case you've just joined the call now, if you have any questions during the talk, I recommend you put them in the chat, and I will address them in the middle of the talk somewhere if there is enough time. Otherwise, we will take questions at the end. I just want to make sure I have enough time to cover everything of interest. So let's dive into the topic. And actually, as I sort of hinted, one very good way of introducing the topic of categorical deep learning is to first have a good level of background in geometric deep learning, which is a framework that predates categorical deep learning by a few years, right? So let's first talk a little bit about the foundations of geometric deep learning, which we can then use as a stepping stone to go on to categorical deep learning. And on this slide, you can see some details as well as a link to access the work on GDL if this is something you are not familiar with. This is work I've done with Michael Bronstein, John Brunner, and Taco Cohen 3 years ago. So the fundamental concept inside geometric deep learning and how we use it to organize all of deep learning architectures is the concept of symmetries. So the main idea of a symmetry is that it is a transformation that takes an object and doesn't fundamentally change that object, at least from the perspective of what is the task that we are currently solving. And as we will see, this turns out to be a pretty powerful framework for deriving a lot of the standard layers that we use in deep learning today. So specifically, here is just, I feel like this is an example. This is a concept that is best visualized with an example. So here we have some data that, say, a deep learning model might ingest, which lives on a triangle. And we put features in the 3 corners of the triangle. And depending on what it is that we want to classify over this triangle, we might say that if we were to rotate the triangle or horizontally flip the triangle, it is still the same triangle. We're just observing it in a slightly different way, right? So this symmetry group of this collection of transformations of these 120-degree rotations and horizontal flips can be seen as a collection of symmetries of the triangle. Of course, for certain problems, these might not necessarily be symmetries. In the case of image data, you might sometimes consider a horizontal reflection to be a symmetry, but sometimes you might not. Similarly for vertical reflections. So if I give you a picture of a 6, if I do a vertical flip, then it's no longer a 6, it's a 9. So sometimes it's a symmetry, sometimes it's not. But this is a great way in which we can formalize what are the transformations of an object that will leave them unchanged for all intents and purposes. And one thing that's really great about the concept of a symmetry is that once you kind of collect axiomatically all of the things that a symmetry must be in order to leave an object unchanged, you end up discovering that you can talk about all of the transformations inside a collection of symmetries as a very well-known mathematical construct, which is a group. And here I give you all of the main axioms that a group must satisfy. So a group is a collection of objects and a binary operation between them that must satisfy certain properties like associativity. So if I have 3 different symmetries, I can decide to compose them in 2 different ways. I will still get the same transformation at the end. The parentheses don't matter. There's always an identity transformation, right? If you don't do anything to the object, it is by definition unchanged. So there must exist an identity. And also there must exist inverses, because if my transformation hasn't changed the object, it has to not delete any information about that object. So I must be able to come back from where I've started. So there must exist a unique inverse. And also there must be a closure property. So if I have 2 different symmetries, if I were to compose them, I would still get a symmetry as a result, right, if I do this composition. So this is another important property that, that symmetries must satisfy. Okay. And it turns out once I have this concept of a group of symmetries, I can then use it to describe constraints on functions. And those constraints turn out to be very intimately tied with how we construct certain classes of neural networks. The first important such constraint is group invariance. So if we say that it truly is exactly the same object, and I want to classify it exactly the same way, for example, in the case of images, you have this picture of a bug, which if I apply a shift to that picture, it is still a bug. And if I have a classifier, it should give me exactly the same answer in those two cases. This is a property I can formalize as group invariance. So here at the top, you can see the definition. Any function mapping your data to some output set of classes is invariant to G, where G is a symmetry group, if no matter what group transformation I apply to the input, I still get exactly the same output. So in the case of image classification, this allows you to say, what does it mean for an output of a function or a neural network to not depend on, say, shifts of an image? You can also define a more fine-grained notion of group equivariance, where actually things are allowed to change as the input changes, but they change in a predictable way. Specifically, for any group action you have, it doesn't matter if you apply it before or after applying your function. So in this particular case, say in the context of image segmentation, which is one very standard domain in which we talk about equivariance, once you shift your input image, obviously your segmentation mask has to change as well because you've changed what the input image is. However, because you've shifted your input image, if it's a proper classifier that respects the structure of the image and the symmetries of the translation, as most CNNs do, then the output segmentation mask should shift in exactly the same way as you do on the input image. And I have this animation, which hopefully you're able to see as I go back and forth from my slide, that one great property of 2D convolutions is that as you move a particular image that you care about, the resulting features that you extract move together with the image, right? And actually invariance can be seen as a special case of equivariance. So these two properties are really fundamental when it comes to building architectures in geometric deep learning. And in our work, we actually show that if you do some combination of these equivariant layers with some nonlinearities and potentially a pooling layer at the very end, if you care about predicting stuff over the whole domain, this is actually enough to rediscover pretty much all of the popular architectures we use today. So CNNs, GNNs, deep sets, transformers, LSTMs, they can all, like the main constraints that those architectures satisfy, can all be discovered by choosing the right domain your data lives in and the symmetry group that you want your architecture to be equivariant to. So CNNs, for example, are a direct solution of searching for translation equivariance on grids. In fact, it's a well-known fact from signal processing that all the layers that are linear and translation equivariant on grids are exactly convolutions. Like, this is a known fact. No other layer other than a convolution can be a solution to this constraint. And for some other architectures like GNNs on graphs, we have similar solutions where we can find the basis of all possible graph layers that can solve a problem on graphs that is symmetric to permutations and so on. But what's really cool about the blueprint is that it doesn't just allow you to talk about popular architectures using the framework of which domain you come from and the symmetry group you choose, but it also allows you to talk about some more exotic architectures that rely on some more interesting symmetries. One of the main examples of this include rotations and translations, which initially led to architectures like spherical CNNs, which have rotational symmetry on the sphere, which is very important when you process data that comes from the surface of the Earth. But also nowadays, especially in biotech, a really popular class of models, these Euclidean equivariant GNNs, which have a permutation symmetry to the atoms in your molecule, but also symmetry to any Euclidean transformations you might apply to that molecule, like rotating it, translating it, reflecting it. You should expect things like the energy of the molecule to not change in a vacuum as you transform it in this way. And these equivariant GNNs are architectures that can help you deal with those situations. So it's a pretty popular blueprint, and it can explain a lot of things already, or at least semantically explain the constraints. And here is just a recap. So in geometric deep learning, we design neural networks that are fully resistant to symmetries, either in an invariant way, such that symmetry does not affect the output at all, or equivariant way, which is a bit more generic. So symmetry on the input affects the output, but it affects it in the same way. However, symmetries, like the reason why we need to go beyond what GDL can explain is because symmetries are actually not the whole story. And to see how they're not the whole story, I'm going to give you again this snapshot of the symmetry group axioms. And specifically, I want you to focus on two conditions that symmetry groups must satisfy. The first one is this existence of inverses. So it means that the operations you want to align your neural networks to have to be invertible, like they cannot lose any information. And secondly, you have this closure property, which means that every transformation must compose with any other transformation. And these two properties are pretty useful. They are restricting a little bit the mathematical objects so that you can solve the constraints a bit more easily, but they do not model all possible transformations that we might want to care about, because we won't always want to align our neural networks with computation that is invertible, and not all pairs of computations we care about will be composable. So just from those two properties, we might say we might want to go beyond what symmetries can explain. And this is especially true if you want to model how neural networks align to general computations, such as classical algorithms. So if you want to build yourself a model that can, say, robustly execute some computation, which nowadays we tend to associate with reasoning in large models, you might need to talk about operations that can delete some of your data, or operations that can only compose if the output type of the first one matches the input type of the second one. So generally, it sounds like we need a language that's a little bit more general than group theory. And it turns out category theory offers such a perspective. Now, how do we go from groups to categories? Well, specifically here, I need to outline some of the main axioms that still hold in category theory. So the main difference now is that we no longer have the constraint of invertibility, and we no longer have the constraint that all pairs of transformations must compose. The only thing that remains is that if I can compose something, it must be possible to do it. That's really the main thing that categories still assume. So let's dive through some of the main axioms that we are working with when we assume that our transformations come from a category. So a category is a collection or a universe, depending on how you prefer to label it. I deliberately use these words rather than set. You'll see in a few slides why it's important to not use the word set. So a collection of objects and a collection of morphisms or arrows between them. So you can think of these arrows as your transformations, such that, first of all, every single object must have an identity morphism, which is unique. So some ID for that object, which maps A to A. Then if you have a morphism from A to B and a morphism from B to C, there must exist a composition that takes you directly from A to C. So the transitive closure must always exist, right? And there are some expected axioms on what happens when you compose with identities, right? So if I have any morphism from A to B, I will get that same morphism if I pre or post compose with the relevant identity, either IDA or IDB, depending on which side I'm composing from. And both of those compositions will be the same as the morphism I've started from. And also, you need to have associativity. So if I have any F, G, and H that are composable morphisms with each other, it doesn't matter which pair I compose first, I will still get exactly the same composed morphism in the end. And you typically study these morphisms and structures of them by drawing these commutative diagrams. So you have objects as basically nodes in a graph, and you have arrows as basically directed edges connecting these different objects together. And what do we mean by commutative diagram? We mean that when we draw a diagram like this, any pair of paths that map an object to another object will give you identical morphisms. So here you can travel from A to C either by taking the morphism G circle F, or by composing first F and then G. By definition, by axiomatic definition, these two need to be exactly the same morphism. Okay, so one thing that's very important to note immediately is that by doing things in this way, we have generalized what a group can offer us. Because if you remember, in the definition of a group, there was exactly one identity. Here we have a separate identity for every single object. Also, not all morphisms need to be invertible, and not all pairs of morphisms can compose with each other. Only the ones where the output type of the first one matches the input type of the second one, right? So this already gives you a more general construction, but hopefully it's a construction that you can reason aligns well with this kind of general computable things, right? So you can imagine that in a computer, you might have programs that don't preserve everything about your input data, but typically a function of one output type can be a useful input for another function that accepts that type as input, right? So this hopefully is a structure that's not something that's unreasonable to assume. But one thing that's very critical is that we never assume knowledge of what's inside the objects. This is critical. So objects are really just abstract blobs to us. And this is important because it actually allows us to just look at the structure of the computation, so what the arrows look like, and we don't get bogged down in details about what's inside the objects. And that's why category theory tends to be generally an excellent recipe for discovering connections across very disparate areas of mathematics. So to illustrate this, I will show you a very standard example, which is known as the set category. It's one of the first things you learn when you start the category theory course. So as I mentioned before, in a category, you have to define what are your objects and what are your morphisms. So in this particular case, our objects are sets and morphisms are functions between those sets. So here you have one example of a set A and a set B and the function that maps elements of A to elements of B, right? And this is, hopefully now it's clear why I didn't say that objects are in a set, but objects are in a collection or a universe. Because if I said objects are in a set and objects are themselves set, you can end up with issues like Russell's paradox, right? If you allow yourself to have sets of sets. So basically the reason why I use the word collection is just to avoid these kinds of paradoxes. There is, in fact, a nice construction that you can use to avoid them, but saying sets of sets is something that gives you problems. So, but one thing that's important, though, is that you don't actually see what I showed you in the previous picture when you draw a part of the set category. You only see an object A and an object B, and you see an arrow F connecting them, right? So you might wonder whether this abstraction, even though it's kind of useful and elegant, whether it might accidentally drop a ton of data that you might need to make decisions. Well, I'll now show you a result, which I think for category theorists, it's a fairly trivial result. But when I first saw it, it was a bit mind-blowing for me because it showed how you don't need to know anything about what's inside A and B. You can just look at the arrows, and I can still tell you about everything that's inside A and everything that's inside B. So let me show you how. We're going to start by discussing the special set, which has exactly one element. For those of you who come from functional programming, you might know that we sometimes denote this set by open closed parenthesis or unit. It's a special kind of type which is used just for functions that don't return anything. So what can you tell me about morphisms from any set to the unit? How many? So this is a question for the audience. You can write it in the chat. So how many morphisms are there from any set A to the unit set? Any thoughts? Yes. I see several people have written 1. Yes, the answer is exactly 1. So it is the function which maps every single element of the first set to the unique unit element. And in fact, this property, the fact that there exists exactly one morphism in set that maps each set to that set, is what uniquely defines the unit set. Obviously, up to isomorphism, we can have many different sets with exactly one element, but you can identify them structurally because they look exactly like this, right? So if I want to abstract away in a categorical picture, I'm basically pattern hunting for a subgraph that looks like this, right? So my unit set is any object that looks like this when you look at all the other sets inside the category. And basically now we've been able to identify what this one element set looks like up to isomorphism just by looking at the arrows, right? For those of you who come from category theory, you'll know that this special type of object is what's sometimes known as a terminal object. But now that I've identified the unit, I can now look at things from the other direction, right? So what can you tell me about morphisms from the unit to any other set B? And here I've deliberately numbered the elements of B just to illustrate my point, but in general, it doesn't matter if they're numbered or not. So in this case, we have this set B of 6 elements. How many morphisms are there from unit to B? Exactly, Ritkesh. There are 6 of them. And specifically, you get exactly one morphism per element of B. Now, this is supposed to be an animation. It will run as long as I'm inside the slide. And actually, sometimes in functional programming languages, which assume that everything is a function, this is how you represent constants, right? Because you can think of constants as functions from a unit set to the set that you care about, right? And each of these morphisms uniquely identifies one element of B, right? So if you look at what the picture looks like now, we've first identified the unit set by looking at the arrows. And then once we know the unit, we can look at all the morphisms from unit to any other set, and voila, we have rediscovered all the elements inside that set. Because for all intents and purposes, every single arrow from unit to B is the same as an element of B, right? So even though I never peeked inside the sets, I just looked at the arrows, I was still able to reconstruct every single set in my category up to isomorphism. And I think this is a pretty strong result. So we're able to detect patterns in computation because we're only focusing on the arrows, where we made this conclusion just by looking at the arrows, and we never looked at the specific of what's inside the data that these arrows are run over. And we've done all of this without really losing information from where we originally started from. And for this reason, it is the opinion of myself and my co-authors that category theory can be a perfect tool for our purposes, and generally a tool that we can use wonderfully to connect many disparate parts of math together. Now, obviously, what I've shown you here depends only on the category of sorry, not finite, but just category of all sets, including infinite ones. When we deal with neural networks, we might want to look at slightly different categories. Specifically, we might be curious about vector spaces and functions that map between different vector spaces. And one standard choice to deal with that situation is to use the so-called vect category, which is very similar to set. It's just that your objects are now not sets, but sets which have which support the axioms of a vector space, right? So you need to also have a space which supports the addition of elements and scalar multiplication, such that the usual axioms like distributivity, and so on apply. What are the morphisms in vect? They're not just any functions, they are linear functions between two spaces. And in fact, the study of vect is exactly the study of linear algebra, which is very convenient for us because linear algebra is the bread and butter of how deep learning models are built. Now, the power of category theory arises not so much when you look at an object collection and morphisms, but actually when you start to allow categories to interact with each other. And just like we can define functions between sets, you can define functors between categories. They map both the objects and the morphisms from one category to another. So how does this work? Let's have C and D be two categories, and I can define a functor that maps objects and morphisms of C to objects and morphisms of D, such that it cannot be just any mapping. It has to be one that respects the compositional structure inside the original category. So what does this mean? If I use my functor to map any identity of an object, it must map to the identity of where that object lands in the other category, right? So this means that the structure of the identities is preserved. Similarly, if I apply my functor to any composition of two morphisms in the first category, you have to get the same result as if you were to first transform the two morphisms separately and then compose them in the second category. So these two simple rules are necessary to preserve the structure which is located inside the first category when you map it into a second one. Also, one thing we will talk about quite a bit today are functors that map a category to itself, so-called endofunctors. They'll be very important for a lot of the constructions we'll talk about today. So I feel like the concept of a functor is something, it takes a few examples to properly internalize it. I don't have a lot of time to show you a bunch of examples. What I can show you is a picture that you should kind of carry in the back of your minds when you imagine a functor. So here we have a diagram showing one category and with just two morphisms and their composition, as we discussed before. So what would a functor do mapping this to somewhere else? Here, I've explicitly delimited what is category 1 in blue and what is category 2 in red. Like basically, if we have any of these like nice triangle-style structures in the first category, a functor should map all of these things to parts of the second category such that the nice structure is preserved. That is really what these axioms are all about. And you need to have a functor like this, otherwise you cannot like reasonably use it in any other proofs that you're going to use. And one thing that's very important to note, though, of course, is that this doesn't mean that A, B, and C must map to 3 different objects. You can equally as well have a collapsible functor where all of these 3 objects map to the same object on the other side, but still the corresponding morphisms and their compositions must map in the same way, right? So there should be a triangle-like structure, even though the edges of the triangle are exactly the same thing, right? Another good way to think about this is it's basically a way to encode analogies. And John Bayes has this very nice quote where he said that every sufficiently good analogy is yearning to become a functor. So this is the concept of functors. Another concept that's going to be very important for what we're going to do next is the concept of a natural transformation. So much like functors allow you to connect 2 categories together, a natural transformation is a concept that allows you to connect 2 functors together. And this is actually one of the most powerful concepts category theory has to offer. Eilenberg and MacLean, the people who discovered category theory, in fact, invented functors for basically the sole purpose of defining naturality conditions. So how does that work? Well, we take 2 different functors, f and g. They both have to take the same input category to the same output category. And inside these 2 functors, we define a natural transformation alpha, which we denote by this kind of functor 1 double arrow functor 2, as follows. So how does it work? A natural transformation is basically something that looks at all the possible morphisms and where they map using these 2 functors, and they connect the outcomes of those 2 morphisms, right? So for every single object inside our initial category, a natural transformation specifies a morphism, alpha x. So a natural transformation is not one morphism, it's a collection of morphisms, one for each object in the first category. And that morphism connects the output of the first functor to the output of the second functor in the second category, and in a way that will connect the outcomes of the morphism mapping in an appropriate way. This is something that's best visualized, once again, using a picture. So let me show you what this looks like. So how does a natural transformation work? You take any morphism x to y in your initial category. And as we said, we're connecting 2 functors. So we have functor f and functor g. They will both map x, y, and this morphism to specific places in the second category. And you'll see we have these 2 lines connecting f of x to f of y and g of x to g of y. So the natural transformation is just the unique arrow that allows me to connect these 2 in a commutative diagram, right? Such that, say, when I'm starting from f of x, I can either first apply f of f and then the corresponding alpha in y, or I can first apply the alpha in x and then run g of f and end up in exactly the same place with exactly the same function. So that's really what the natural transformation is. When you take 2 different functors, they'll map this arrow to 2 different arrows, and the alphas are really what connects those 2 arrows together. But you need to define one for every single object, one for x, one for y. And often when you draw natural transformations and the rules that they support, you'll typically just draw this square in the middle. I've here deliberately drawn where the 2 functors take x to y, just to kind of make the picture more full and so that you understand where the square comes from. But essentially, this is something that typically is omitted when you draw naturality conditions. So just so you don't get confused if you see this somewhere else in literature. So this was a very quick whirlwind tour to what category theory offers us, and generally what you need to do in order to specify various things. So in order to talk about a category, you need to describe me what are the objects and what are the morphisms between those objects. And in case it's not obvious or trivial, how those morphisms compose and what the identities are. If you want to specify a functor, you need to tell me what are the 2 categories that the functor relates, and you need to tell me how the objects map to each other and how the morphisms map to each other between the 2 categories with that functor. And to specify a natural transformation, you need to tell me what are the 2 categories that are being related by the functors, what are the 2 functors that you're relating with the natural transformation, and then for every single object in the first category, you need to specify a component morphism in the second category, which connects those 2 arrows that we showed you before. Okay, Now, using all of this, we can finally define the first important object that we can use to derive categorical deep learning, and that is the concept of a monad. Now, in order to build geometric deep learning models, as I told you at the beginning, we needed to reason about actions of a group element. And you can make a categorical version of group actions by using a special kind of endofunctor known as a monad. Now, for those of you who have done any functional programming before, or Haskell or OCaml or languages like this, you probably heard about the concept of a monad. It is a concept that is very universal, but quite tricky to explain, as evidenced by this plot showing the amount of monad tutorials per year, which is growing quite significantly. And sometimes explanations of monads just defers to saying it's just a monoid in the category of endofunctors. I don't see what the problem is, right? So it's a concept that's not particularly simple to explain, but it is one that's quite important when you want to talk about composed computation, and it is one that really forms the cornerstone of what our categorical deep learning proposes and how it generalizes geometric deep learning. So let's try to define monads for the context of this talk. So this is me adding yet another monad tutorial to the sea of possible monad tutorials. Hopefully it doesn't add to the confusion. Maybe it even helps clear some things up. So how can we define a monad in a category? It is a tuple of three things. The first thing is an endofunctor, so something which maps object in C to M of C, right? And you can imagine this, we'll see this in a bit, you can imagine this as a sort of container which encapsulates certain kinds of computation. And together with that endofunctor M, you also need two special natural transformations, one called return and one called join. The return one connects the identity endofunctor to M, right? And the second one connects the composed endofunctor, M compose M, to just M, right? And this maybe at first sight looks very confusing and doesn't look like it necessarily leads anywhere, but if you bear with me, I will try my best to like unpack it and make it make sense. The way in which I like to think about these things, and it took me a while to internalize this myself as well, is you can think of M, because remember, an endofunctor will map some object X to M of X, right? Some different object inside that same category. And you can think of it basically as a container. Like it's saying M of X means I want to perform computation M on the object X, right? And these two natural transformations, eta and mu, as we discussed, how do you define a natural transformation? You define it by specifying these component morphisms in every object X, right? So to define eta and mu, we need to talk about eta X and mu X for every single object X. So eta X, because it maps from identity endofunctor, the left-hand side is just X, right? It's identity. And the right-hand side is M of X because it's connecting it to the M endofunctor. So really, you can imagine this morphism as just telling you how to create a new container which just contains X but doesn't really compute anything on it, right? So it's like it's creating computation on X but without actually doing anything, right? And mu is something that allows you to reduce two nested computations into just one computation. So it's something that does a little bit of execution effectively. So hopefully this makes sense. And of course, you cannot just take arbitrary natural transformations. They must be done in a way that certain properties are satisfied, such that when you use return to create blank computation, if you then use join to reduce that blank computation, you should end up exactly where you started from, right? Because we said return doesn't add any new computation. It's just a wrapper, right? And similarly, if you have triply nested computation, it shouldn't matter in what order you do the two joins. You should end up with exactly the same thing at the end, right? So those are the two rules that these two natural transformations must satisfy in order for this to be a legitimate monad. But hopefully these rules make sense, right? And to give you a concrete example of what a monad looks like, the standard example I like to show is the power set monad. So here the computation you're representing is, I want to represent my set using its power sets. So all of the sets contained inside it. So how does this work? P is my endofunctor, and it maps sets X to their power sets, right? So power sets are themselves sets, so they're also an object in set. Therefore, P of X is an endofunctor. And what does it do with functions? Well, if you have a function from x to y, p of x maps it to p of f, which just applies that f to every single subset of x, giving you subsets of y, right? Now, what would the natural transformations look like? You need first the return, which takes any set and returns a power set with no particular extra computation done. So really, this just replaces x with its power set and does nothing else, right? And mu takes a power set of power sets. Well, how do you go from power set of power set to just one power set? You just perform the big union, right? You do the union of all of the inner sets to reduce your power set of power sets to just one power set level. And using this, we can actually describe group actions, which is really the crux of where geometric deep learning came from. So specifically, how can we describe group actions as a monad? We use this endofunctor g times blank, which, how does it work? It's an endofunctor which maps a particular set to products of g times that set. So g here is the group of symmetries that we care about. And specifically what this monad means is it's telling you I have a g and an x. It means I am intending to execute group action g on data x. So for example, translate elements in x or rotate x or something like this, right? Depending on which symmetry group you're working with. And what does it do to functions? If you have any function from x to y, it basically just maps, I want to apply group action g to x. Now I want to apply group action g to f of x. So it kind of leaves the group element alone and applies the morphism just to the data. So what would the natural transformations look like in this case? Well, first of all, the return. So that, as we said, needs to create a group action container which does nothing. So really, for any element, you just do E of x, right? Where E is the identity transformation. So it says, basically, I've wrapped my my set into something containing the identity, which is now a proper wrapper of I intend to run some group action on this. It's just that that group action is identity, so nothing will happen when I actually execute this computation. And as you might expect for the join morphism, if I have, in this case, I have now g times blank. So I have a nested group action application. I want to apply group action g on the application of group action h on x. I can reduce that to just one wrapper by doing the composition of the two group operations, right? It's the same as saying I want to apply g compose h to my inputs x. So this is how we can talk about group actions, which were the crux of geometric deep learning rules, as just monads. However, the mu and the g times blank, the monad elements, they just tell you how to compose the group actions, but they're not actually running the group actions yet, right? This just allows you to build a container. In order to actually execute the group action, so to do g.x or something like that, we need one extra piece of machinery, and that is a machinery known as an algebra. So generally speaking, if you have a construct that allows you to execute computation, they are typically known in category theory as algebras. And the reason why they are a bit special is because and why you need a special kind of construct for it. Why cannot you just represent it using the monad? Because computations might execute differently depending on what's the set you're working with. So for example, imagine I'm modeling permutation group actions on set. They might act differently depending on whether you're transforming a matrix of node features or an adjacency matrix of a graph, right? Because if it's node features, which is of shape nodes times features, you apply a permutation action by just multiplying with the permutation matrix on the left-hand side. Whereas if you have an adjacency matrix of shape nodes by nodes, you need to now permute both the rows and the columns of this matrix. So now suddenly the execution is different, right? So the specific way in which you transform your data differs depending on what's the object you're transforming. So algebra is something you need to define relative to an object. So every single object in set will maybe transform differently when you apply group actions to it. So now we can define this notion of an algebra for a monad, which is defined on a carrier object A. So in this case, A could be either node feature matrices or adjacency matrices. And you'll have this special morphism called a structure map, which allows you to do the actual reduction from M of A to just A. right? So this is, if M was our group action monad, this structure map would just reduce it to whatever happens once you apply the group symmetry to the object. Of course, this cannot be any arbitrary mapping. You must do it in a way that certain diagrams commute, and these are the ones that you see on the slide here. So specifically, if I take an object, I wrap it in a blank computation, then my structure map needs to reduce to exactly the same object. So these two need to be equal, right? Yes, I do believe that XLA lowering out it can be seen as an analogous operation to what we're doing here. So yes, that is correct. Similarly, if you have doubly nested computation, you can either decide to do the join first and then do the algebra execution, or you can do 2 levels of algebra executions and you should still end up with exactly the same outcome. So these 2 diagrams need to commute. Hopefully they make sense. They say that certain operations are interchangeable when they need to be. And finally, I can use this to construct executions of group actions. So let's do a simple example. Group actions are actually exactly the algebras for this group action monad. Let's imagine I want to model translations on images, which is the classical example that people use when defining convolutional neural networks. So here, your group G is the translation group. So that's just integers times integers, which tells you how much you shift in the width axis, how much you shift in the height axis. Acting on a grid of pixels. So your carrier objects will be like, if you just have one feature per pixel, it will be real matrices of shape, width times height. And your structure map for that algebra will then look something like G times carrier set to just carrier set, right? So, and that is basically literally the translation action as you typically would define it, right? So this translation operation acts on 2 shift values and your matrix of pixel values to perform the readout at the right pixel coordinate, right? Now, of course, in order for this to be a symmetry, we typically assume that these are cyclical shifts. So typically there should be a modulus here when you take the subtraction. So if you shift by more than the index value, you need to roll around and read from the other side of the image. But if you define it properly in this way, you'll end up with a circular translation, which is exactly what CNN layers are equivariant to. And this now allows you to talk about the inputs and outputs of neural networks and group transformed versions of them. But to actually talk about a neural network layer, you need to describe a transformation between these 2 carrier objects. And that is the final part of the puzzle that we need, which is a homomorphism of 2 different monad algebras. So specifically, we need to talk about a mapping between the input space and the output space for our neural network. And those 2 spaces might be different, so different dimensional real spaces, for example. So for each one of them, we define a separate algebra, right? Each algebra tells you how that particular real space is applied group actions on, right? So you have M of A and M of B for 2 different sets. And we say that something is a monad algebra homomorphism if it's a mapping between these 2 objects, A and B, such that this diagram over here commutes. So this now means that I am either able to first transform the first object, then run my function, or run my function and then transform it in the second space, and I'll get exactly the same result, right? And if you plug the group action monad in that diagram, so this diagram here is exactly the same as the diagram in here. I've just plugged the specific monads and algebras for a translation group. You'll end up with a commutative diagram giving you rules for a translation equivariant neural network, right? Because here we have 2 different spaces with 2 different dimensionalities in your pixels. On the left-hand side, it's k-dimensional. On the other side is k-prime. And your convolutional network maps from the k-dimensional to the k-prime dimensional space. And you want to build that function such that it is irrelevant when you choose to do the translation operation. Do you do it in the original space or you do it after in the output space, right? So this here is exactly, if you translate it into a constraint on the function, it turns exactly into a constraint like this, which is exactly shift equivariance. So this is the crux of geometric deep learning on images. And this rule generalizes to any pair of algebras for any group action monad. It just ends up looking in more generic form like this, where you have A and B as two different kind of group representation outcomes. And this basically now derives all equivariant maps, i.e. all of geometric deep learning. So really, the main takeaway from this part of the talk should be equivariant maps, the bread and butter of geometric deep learning, are nothing else than group action monad algebra homomorphisms, which is maybe the most words that are loaded that I've used in succession, one after another. But hopefully, like, it is clear now why that sentence makes sense, rather than just saying something like a monad is just an endofunctor in the category of monoids. I don't know what the problem is, right? Or the other way around. So this is one of the main ideas. We've rediscovered all of geometric deep learning for this particular special case. But and you might wonder how to resolve these constraints. As you might expect, you can resolve for, say, linear equivariance by mapping this diagram into a category like vect. And this then ends up in exact weight sharing constraints, which you can use to derive convolutional neural networks. I won't go into a lot of detail on this because this is already a very standard thing to do in geometric deep learning. What I want to show you in the remaining 5 to 10 minutes is how now we can go beyond geometric deep learning, because nowhere in the definition of these homomorphisms did we need to use these special axioms that monads have, right? So we can define algebra homomorphisms beyond just monads. We can talk about any endofunctor which doesn't have the monad constraints. So you can define an algebra for an endofunctor as, once again, a pair of a carrier object A and some structure map which performs evaluation. And there's no structural constraints you need to do this time. And in fact, examples of these kinds of algebras are abundant in computer science. I will just give you one example to show you what we can do already very simply with this framework, with the same diagram, without really lifting a finger compared to what we did with group actions. So we can define an endofunctor, this 1 plus A times blank, which is a really special endofunctor because you can use it to derive lists, a very standard type in computer science. So specifically, you can define a pair of maps, nil cons. The nil map maps the one object, and the cons map maps the A times blank part. And lists are exactly an algebra for this endofunctor. And they define lists in this inductive way, like you might see in Haskell, where this one part is the empty list, so 0-element list nil, and the part of A times blank is basically the part that tells you the first element coming from A times list of A, which is the remainder of the list, right? So this is an inductive way of defining lists, which is very common in functional languages, and it can be related exactly to algebras for this particular endofunctor. And you can define now a homomorphism between two different endofunctor algebras. The diagram looks exactly the same as what we did for monads. I've just deliberately changed the M to an F to denote that it's no longer a monadic structure necessarily. And if you just, this same diagram here, if I choose to plug the list example that I just gave you, I can now define maps from list of A to any particular output type X I care about, such that the structure of the list, which is contained in these nil and cons algebras, can be preserved with any other R0, R1 maps that I want to preserve. And these kinds of functions, mapping list of A to any output type X, you might know them from functional programming as folds. Folds are a very standard construction in functional programming. And if you try to resolve the constraints of this diagram, you actually end up with equivariance constraints for lists, right? So if you want to define a neural network, FR, that takes lists as input and outputs something that aligns with a fold specified by R0 and R1, that function needs to satisfy these symmetry constraints over here. But what's magic about this is that this is very similar in spirit to what geometric deep learning does, but you could never write a diagram like this in geometric deep learning because the act of consing a head to a tail is not a symmetry operation. You're adding more information to a list, which is not something that is in general, that's something you can easily invert in both directions, right? So cons does not leave a list unchanged. Therefore, this type of constraint, even though it's a very intuitive constraint for how to build neural networks that take lists and give outputs, you would never be able to specify this using GDL. And this, by the way, you can see it relates very nicely to operations of RNNs. So RNNs might operate very similarly to what you can see here. Now, I want to very quickly mention, and then I'm going to take questions because this is really the main result I wanted to show. The picture I showed you so far only allows you to deal with linear equivariance constraints, and it doesn't make your parameters explicit, and this was a limitation of GDL as well. But actually, the framework that I showed you here is capable of modeling whole architectures, weight tying across layers, and parameters, which GDL was absolutely not able to do. But to do this, we need to step from one categories into two categories. The main thing that's different is that we have now objects, morphisms, as well as two morphisms, which are morphisms between morphisms. In fact, we've been secretly working in a two-category all this time, because you can think of a category of categories where objects are categories, morphisms are functors, and two morphisms are natural transformation. Of course, this is something we never made explicit, but it's something that that is in retrospect quite clear. And in two categories, we can model something called parametric morphisms. The para category is very similar to the set category. The main difference is that now you're allowing your functions to also have an explicit set of parameters coming into them. And this should be very similar to those of you who worked with very familiar to those of you who have worked with any kind of neural network specification language, especially languages like JAX, where you're explicitly feeding parameters whenever you invoke a forward pass, right? So now your morphisms depend on this P as well. And you can, as you might expect, compose two morphisms in para by just chaining the parameter spaces of the two. So if you have one function that depends on parameters P and another one which depends on Q, you can chain them by just taking the tensor product of P and Q, and those are the parameters for the whole operation. Again, this is very similar to how, say, JAX would represent composite parameters for a collection of neural network layers. And also, you have two morphisms, which allow you to reparameterize a function to come from a different parameter set, but you need to apply some map R, which maps your parameters from P prime to P. So this now allows you to talk about a connection between a function f and a function fr, which has parameters P and parameters P prime. What's really cool about this reparameterization is that it also allows me to explicitly talk about tying the weights. So if I have a function which contains two sets of parameters coming from a set P, I can force those two layers to have exactly the same parameters by just using the two morphism that uses the copy map, right? So I have just one P, and I use the copy map to send those parameters in both places. So that's also really cool. It allows me to talk about weight sharing not just in one layer like GDL did, but across multiple layers, allowing me to talk about things like recurrent neural networks more easily. The thing that makes things difficult, and I cannot dive into the complexities of this because we don't have a lot of time, is that in all the previous examples we've shown and the constraints we derived, we only dealt with the situation on the far left, where we have a commutative diagram where two different paths are assumed to be the same. But now if we allow ourselves two morphisms, we can end up in a lot of different situations where it's not quite a commutative diagram, but I can find a two arrow linking one path, morphisms in one path to morphisms in another path. So there's four different situations we need to take into account. So depending on what kind of situation we have, we can be either commutative or pseudo-commutative or lax or colax commutative if there exists a two morphism that takes us from one path to another. And kind of making sense of this sea of complexity and situations is something that's very much open to future work. But in our paper, we showed that already, if you only focus on lax two algebras, it is sufficient to recover a lot of the variance of weight sharing you would see in recurrent neural networks or recursive neural networks, or even neural networks that align with automata like Moore and Mealy machines. So it's a really powerful construct that suddenly allows you to talk about not just the semantics, i.e. the constraints we attach to models, but also derive exactly the weight sharing patterns that you see in those architectures, which is pretty cool. We used exactly the same gadget as we used for the geometric deep learning part of the talk. The main difference is that now it's in a two category and we need to deal with laxness, but it looks exactly the same, which is pretty cool. So this is only a snapshot of a very rich picture of categorical deep learning, which we only formed recently. And we put out all of the materials on categoricaldeeplearning.com. We warmly invite you to contribute, whether you come from machine learning or applied category theory. We want to hear from you, and we want to work together on this. And if during your journey you ever get stuck on a term and you'd like to understand it better, I would say NLab is probably the best resource. Think something like Wikipedia for categories. Just be careful, because NLab was written by mathematicians for mathematicians, and it usually assumes that you understand everything else that you see in a particular article. So beware of rabbit holes. I end up in rabbit holes on NLab a lot, where I start from one concept, then I jump into another concept, I jump into another concept, and I end up 2 hours later not really understanding anything about anything. But if used properly, it can be a remarkably powerful resource that you cannot find anywhere else. So that was my last slide. Thank you very much for listening. I hope you enjoyed it. And I'm happy to sit around and take any questions if you have them. Thank you.
Right. Okay. Thank you, Petar. Let's go through the questions in the chat first and then on the queue. Does that sound possible? So we first have, let's see. Oh, well, there is a question which is, are you going to share the slides with us?
Yeah, I'm happy to share the slides. I will. Right. I can send them to you later if you want.
Right. Then there is a question from Ivan that says, is it analogous to XLA lowering from stage out computation in JAX?
Yeah, I answered this during the talk, and I said yes, basically. You can imagine it.
Right. Then there is a question as well, which says, right. Could you give a hint of a concrete engineering application, perhaps a new architecture?
Right. So for this particular, I mean, there's a few things that we showed here which are already things that haven't explicitly been pointed out by previous frameworks. So things like list equivariance or tree equivariance constraints, and then resolving them to get recursive and recurrent neural networks that align with automata. I think these kinds of constructions haven't been shown before in geometric deep learning for sure. And aligning neural nets to automata means that you're going to be able to have better execution properties for those kinds of automata computations than from, say, a simple transformer, right? So already in, like, our paper is mainly a position paper. It doesn't really present results that are new to category theory, but already with what's in there, you can see a few sketches of how to make architectures that I don't think have been described in some previous papers. So yeah, take a look at the appendix for our paper and you'll find some interesting examples there.
Right. Right. There is a question from Pensheng which says, does the new theory explain the purpose of rotary position embeddings in the transformer or ResNet bypass?
Right. So I would not say that we have an exact explanation for these things right now, but I would say that the theory should be able to get us there, because I mean, the basic theory can already talk about the basic positional embeddings because they can be related to the eigenvectors of the shift matrix, which corresponds to the discrete transform and things like that. These relative rotations, I mean, to some extent, I would say probably even basic geometric deep learning could explain this, but maybe with a framework like this, we can arrive at it in a more principled way. So yeah, we don't have it yet, like a concrete explanation, but I think it's powerful enough to explain it.
Right. Then another question from the same person: if the given opportunity to build a CAT for AI framework from scratch without historic influence of JAX or CATGRAD, what new capabilities would you prioritize, and what type of system will be needed? What type system, sorry, will be needed?
Yeah, that's a very interesting question. Yeah, I would say the main thing that the main place where we get headaches and we would like to be better at it, and what we might want to model with these frameworks better are, what's the bread and butter of current architectures like transformers. It's, being able to do shape inference, Einstein summations, and just generally reason about shape algebra properly. So yeah, something that puts properly interval arithmetic and shape algebra as a first-class citizen would be something that would be very nice to have. JAX obviously is a step in the right direction, but even JAX is, I think, not completely free from the confines of Python when dealing with these kinds of situations. So I'm sorry if this is not the right answer. It was a bit of a vague question, so I tried to answer it the best way I could with the knowledge I have.
Right. Another question is, do we have a categorical approach for grammar for NLP?
Right. So I haven't personally worked on this, but I would check out some of the work that Idene Bradley is doing. She's done a lot of work trying to categorify concepts in language models. And actually, the folks, so you mentioned Bob Koech in your comment, he actually, with the folks from Quantinuum, organized a few quantum NLP conferences at Oxford, and there are talks from those that are publicly available. I attended one of these myself, and I think there were quite a few talks talking about categorifying grammars. So I think you might want to check out some of those talks to see how far people have gotten in using category theory for grammars. But I have not personally worked on this.
I have a question actually, which is related to possibly applications on algorithmic reasoning in a way. So yeah, you mentioned how categories remove this constraint on invertibility and certain types of compositionality in that groups have, right? And in algorithms, actually, you do have that, right? Like if you run DFS, you find the path, you find certain path or something, or let's say BFS, then you could possibly, like, given the final output, you can have several graphs that have the same thing, right? That give the same output. And are there limitations there related to possibly different outputs that are equally valid?
Right. So yes, definitely. Currently, this is a great point, actually. I worked with some master students recently on this exact problem. Basically, the idea is currently we are sidestepping that issue entirely by tie-breaking the algorithms. So we sort of force it when an algorithm has multiple equally good choices, you always have to pick a node with the smallest index or something. So in this case, we kind of force ourselves to have a unique target. But I do agree with you that this is not where we want to be in the end, and we need to deal with ambiguity in what the answers are going to look like. I am not completely certain, like I'm sure that some aspects of this framework can help with those situations as well. Currently, what we sort of played around with is to try to distributionally model the solution. So do things like, predict the probability distribution over all correct next steps, or try to learn something like a energy-based model to, like, rather than just predict the steps, try to minimize the energy of the solution, which for some tasks like sorting, you could define energy by, say, the number of inversions in your array or something like this. So there are directions that might help you work your way around it. But currently, yeah, we're deliberately focusing on unambiguous computation. And to be honest, already that problem is really, really hard. So I think it will keep us busy for a while before we start to talk about multiple solutions. But I do agree it's something that needs to be worked on a little bit more.
Right. And also about algorithmic reasoning, this is general, maybe not only about category theories. Do you think if you have enough data of, let's say, runs of an algorithm, or even maybe you don't know the algorithm, but you have data, can you generate an algorithm that does it? Let's say a new algorithm that might, or let's say, okay, so generate something, right? And can you prove that the network learns a new algorithm? And can you formally prove that this is an algorithm, that it's correct?
Right. So this is a good question. I think that out of the box, probably with the tools we have so far, you cannot do this. However, we've done things like this using like a two-step process where you first kind of teach a network to follow the traces, and then you constrain the network to go through a bottleneck so that the things that come out of it are like low dimensional. And then we've been able to use like first-order logic inference tools to try to figure out what is the logical formula that this model is implementing, and basically realizing that it has learned a particular algorithm for parallel coloring or things like that. So this is a paper we published at AAAI a few years ago. It's called Algorithmic Concept-Based Explainable Reasoning. It's a bit more going in the direction of explainability than what we're saying here. But basically, I think at least with a two-stage approach, so some kind of bottleneck training plus symbolic regression, you might be able to extract algorithms out of what these systems have learned. But yeah, kind of out of the box, I think it will be really hard with the methods we have today.
Right. And also, like, I like to think of algorithms as theorems in a way. So do you think you can apply categorical deep learning or geometric deep learning to discover new theorems?
I mean, yeah, I would say so. Actually, the thing that you just said, I don't know if you were thinking about Curry-Howard isomorphism, but I very much live by Curry-Howard isomorphism. To program is to prove, and the other way around, right? So yes, if we have a good method that can reason about algorithmic computation, it should be able to do really well for logical reasoning and vice versa, actually. So yeah, like one will hopefully imply the other.
Right. Okay. Thank you. There is a question in the chat. Let's see. What's your take on the Japanese AI lab called Sakana AI using evolutionary algorithms to create the optimal network topology?
It's an interesting question. I don't know that much about what Sakana does currently. I obviously know what David Ha has worked on over the years, and I've been really impressed by, just low resource, impactful ideas that he's been able to pursue over the years. I think that the approach is pretty cool. I'm not sure how easily it can be related to some of the topics we discussed today, but there is one similarity in that if you do a categorical or geometric approach properly, you'll be able to do a lot more for a lot less. So you won't need as big of a data set or as many parameters or as many anything in order to achieve similar results. Especially, you might also get better out of distribution generalization, which I would imagine Sakana also wants to achieve, but I'm not completely sure exactly where their aims are coming from, right? So that's my take based on the very limited information I have.
Right. And one last question from the chat. Any interesting research idea to explore for a beginner in categorical deep learning for a workshop paper?
Right. I actually think depending on your background, right? But if you come from computer science, like anything to do with automata or to do with simple data structures that you can build using endofunctors, just try to use the framework and try to derive new kinds of neural network architectures, which are not just RNNs or recursive neural nets or these kinds of models. Like, just see how powerful the network is in the wild. Also, there's been a very interesting question that Mircea Petrak posted on Twitter after we released the paper for the first time, which is, your thing can deal with Moore and Mealy machines, but can it deal with Turing machines? I think the framework can deal with Turing machines as well as push-down automata, and extending it just a little bit to also factor for this kind of extra memory on the side of the automaton would be really interesting, and hopefully not a huge step above what we've already written in the paper. So yeah, build a categorical neural Turing machine, and that would be a really cool way to resurrect the original neural Turing machine, hopefully in a way that's a bit more principled.
Okay, thank you for answering all the questions and for the great talk, Petar. Yeah, thank you for everything. Yeah, we will post this probably in YouTube soon. Stay synced.
Thank you all very much once again. And it's the first time I'm delivering a talk in this format to an audience who hasn't seen all of GDL first. So if you have any feedback on how this could be improved or what I should do more fast or more slowly, please feel free to send me an email. I'd be very happy to hear your thoughts. Thank you so much.
Bye.